Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to gravitation and gravity. So in this video we are going to discuss about the gravitational force of Earth. Okay. So far we have discussed the universal law of gravitation in scalar and vector form and also the principle of superposition. So just a quick review of that. So the universal law of gravitation, it states that every object in the universe, it attracts every other object with a force which is called as the gravitational force of attraction. And that gravitational force, it is directly proportional to the product of the masses of the two objects and inversely proportional to the square of the separation distance between them. And it is a central force and it acts along the line joining the centers of the two bodies. So the gravitational force, it is given by F is equal to G m1 m2 by r square. m1 m2 are the masses of the two objects, r is the separation distance between them. Also we discussed the shell theorem. So we discussed shell theorem for point mass present outside the shell or sphere or point mass present inside the shell or sphere. So here the shell theorem will be applicable from the point of view of a solid sphere because we are considering Earth. Earth is a solid sphere, not a shell. So it will be applicable from the point of view of point mass present outside or on the surface of the solid sphere and inside the shell or sphere. So what the shell theorem states for a point mass present outside or on a shell sphere is that if a point mass lies outside a shell or sphere, in this case a solid sphere we are considering, a solid sphere of radius capital R and mass capital M, the gravitational force it attracts towards the center of the large solid sphere. The gravitational force acting on the small point mass, which is at a distance r away, small r away from the center, it acts towards the center of the large sphere as if the entire mass is concentrated at that point. So this is where the concept of point mass comes into play. So please watch the shell theorem video where I have discussed everything in detail. And this gravitational force acting on the point mass which is directed towards the center of this large sphere O is given by G capital M small m product of that divided by r square, again following the gravitational law. Okay, and also the explanation is that the different forces, the vertical forces, the vertical components of the different forces acting due to various small portions on the sphere, they cancel out each other, and the horizontal components, they get summed together. Okay, so this is the reason. Now this I have discussed in detail in the shell theorem video, so I am not going into that in detail. Again, when a point mass is present inside a large solid sphere, the gravitational force only acts by the portion of the sphere which lies interior. So here the shaded portion, it exerts gravitational force on the point mass. So only this inside portion of radius small r, that exerts the gravitational force of attraction, and that is also directed towards the center. And this gravitational force is given by G m subscript r small m by r square. Okay, where r is the separation distance between the point mass and the center of the sphere, and m subscript r is the mass of this inner sphere, okay, the interior region of the sphere, the portion of this large sphere which lies interior to this point mass small m, this white point mass. Okay, so only this region which lies interior to this portion, only the shaded portion, that exerts gravitational force. This region, it does not exert any force on the point mass. Okay, this region does not exert any gravitational force. Only this white shaded portion which I have highlighted, that exerts the gravitational force, and the mass of that is given by the volume of this inner region, that is 4 by 3 pi small r cube, into the density of the sphere. Now again, the important point of shell theorem is that it is applicable only for those objects, those masses which have a uniform mass distribution, uniform mass density. Okay, so this is the thing. Now how we can apply all of these things to find out the gravitational force of Earth? So here we are considering Earth to be a solid sphere. It has a certain radius, it has a certain mass density, average density, which here we are considering it to be homogeneous for simplifying our discussion, so that we can go in accordance with the shell theorem. So suppose we have any mass, any object, let's say we have, since we are discussing it from the point of view of satellite communication, so let us say we have a satellite at a certain distance away from it. So if there are three cases here, okay, so here the three cases are the gravitational force acting on objects which are far away from the Earth's surface, above the Earth's surface, at points near or on the Earth's surface, and at points below the Earth's surface. So we'll discuss all these 3 points. So in the first case we have a point mass here, in this case a satellite, because with respect to the size of Earth, considering the dimension, the size of Earth, satellite behaves as a point mass. Size of satellite is very less as compared to size of Earth. So let us say we have Earth, which we are considering it to a solid sphere of mass capital M, radius capital R, and we have a satellite of mass small m, which is at a distance small r away from the center. And here the condition is that the distance small r is much greater than the radius of the Earth. Okay, it is much greater than the radius of the Earth. This is the condition. Okay, so in this case the gravitational force acting on the satellite because of Earth, it will be towards the center of the Earth. Okay, as per shell theorem, the gravitational force acting on this satellite, which behaves as a point mass, it will be directed towards the center of the Earth, as if the entire mass of Earth, of this solid sphere, it is concentrated at the center. Same as in accordance to shell theorem. Same as in shell theorem. Force acting on the point mass is directed towards the center. Same here also. The force acting on the satellite, the gravitational force of attraction acting on the satellite due to Earth, it is directed towards the center, because gravitational force is central in nature. It is a central force and it acts along the line joining the center of mass of the two objects. And the value of this force is given by, the gravitational force is given by G capital M small m by r square, in accordance to Newton's universal law of gravitation, where capital G is the universal gravitational constant, capital M is the mass of Earth, small m is the mass of satellite, r, small r, is the separation distance between the satellite and Earth. And here small r, that is the separation distance, is much greater than the radius of the Earth. Okay. Okay, so this is the expression for gravitational force acting on an object which is far away, far above the surface of the Earth, at far away distance. The distance of separation is much greater than the radius of Earth. This is the first case. Then we have is the second case, which is at points on the Earth's surface or near the Earth's surface. Okay, say here I will include on or very near to the Earth's surface. Okay, So in this case, the object is very close to the surface of the earth or near the surface of the earth, so that the separation distance is either equal to the radius of the earth or it is almost equal to the radius of the earth. So here the same thing will be done. Here in this expression we'll substitute small r with capital R, and the gravitational force between earth and that object, it will become G capital M small m by capital R square. Here only what we have done, we have equated small r with capital R because the object is near to the earth's surface or close to the earth's surface. So when it is on the earth's surface, this is applicable. When it is near or close to the earth's surface, this is applicable. So in both the cases, this will be the expression. Okay, present on the surface of the earth, I am adding on or near the surface of the earth. This is the expression. We have substituted capital R with small r in this expression. So this is the second case where the object, in this case let's say a satellite, is either on the surface of the earth or near the surface of the earth. So when it is on the surface of the earth, the separation distance is equal to the radius of the earth, capital R, and when it is close to the surface of the earth, very close to the surface of the earth, it is almost equal to the radius of the earth. Okay, then we have is the third case where let's say any point mass, it is below the surface of the earth. Okay, it is below the surface of the earth. So here we have a point mass small m which is below the surface of the earth, such that the distance between the point mass and the center, it is small r. So here again shell theorem will come into play. As per shell theorem, when we have a point mass inside a solid sphere, the gravitational force of attraction is directed towards the center. The gravitational force of attraction acting on the point mass is directed towards the center, and this gravitational force is exerted only by this portion which is interior to the point mass, this shaded region, this white highlighted region. So here also, when this point mass is present inside this earth, so here the gravitational force acting on this point mass, it will be exerted by this portion. Let me use a different ink. This inner region, this region, this region, this red region, and this outside region, this region, let me use, okay, light blue, okay, white. This white region, it will not exert any force on the point mass. This will not exert any force on this point mass small m. This region, the white region, will not exert any force. Only the red portion, that will exert force. Force will be exerted on the point mass only because of this red portion which is interior to the point mass. So here, let's say we have to find out the mass of this inner region. Okay, we have to find out the mass of this inner portion. So let's say we are considering Earth to be a solid sphere of a certain density and certain mass. It has a radius capital R. So the mass of Earth, it will be equal to volume of Earth, that is 4 by 3 pi r cube, the volume of the sphere, multiplied with density of Earth. Okay, volume of Earth multiplied with density of Earth. Okay, so density we can determine as m by 4 by 3 pi r cube. Okay, now the volume of this inner sphere which is inside this black circle, this inner sphere of radius small r, that is equal to 4 by 3 pi r cube, which is the volume of this inner region, okay, Vr. Since we are considering that Earth is a homogeneous mass distribution sphere, so density will remain uniform throughout. So the mass of this inner sphere, it will be volume of that inner sphere multiplied with density of Earth. So that is equal to 4 by 3 pi r cube, which is small r, multiplied with density, which we got the expression here, m by 4 by 3 pi r cube. So when we multiply these two, we get the mass of this inner sphere as m small r cube by capital R cube. M small r cube by capital R cube. Now the gravitational force exerted on this point mass m, small point mass m, which is directed towards the center, is exerted by this inner sphere, mass of this inner sphere. So it will be equal to, F is equal to G mr, which is the mass of the inner sphere. It is the mass of inner sphere multiplied with the point mass m, that is small m. The separation distance between them is small r. So this is the expression, G m subscript r small m by r square. So here when we substitute mr with this expression, m small r cube by r capital R cube, it becomes F is equal to G capital M small m by capital R cube multiplied with small r. This is the gravitational force acting on the point mass small m because of this inner sphere, because the point mass is buried inside Earth and it is at a distance small r away from the center. And this force also, it is a central force. It is directed towards the center of the Earth and is exerted only by this inner sphere, this portion which lies interior to the point mass of radius small r. And the force exerted by this outside region, it is equal to 0. No force is exerted by this outside portion. And this is all in accordance to shell theorem. That's why I discussed shell theorem. Okay, this. So these are the three cases of gravitational force of Earth. First, at points above the surface of the Earth, far away from the center of the Earth at very much large distance, such as the distance of separation is much greater than the radius of the Earth. In that case, this is the gravitational force acting on that mass. When the second case, at points on or near the surface of the Earth, in that case the separation distance is either equal to the radius of the Earth or almost equal to the radius of the Earth. In that case, this is the expression of the gravitational force. And when the point mass is inside this or below the surface of the Earth, the gravitational force is exerted by only the inner sphere, the inner portion which lies interior to this point mass, and in that case the gravitational force acting on the point mass is this much. Okay, in all of these cases, the value of the force, the mathematical expression of the gravitational force is different, but it is always directed towards the center. No matter where the point mass is, the gravitational force acting on the point mass, it is always directed towards the center. Okay, it is always directed towards the center, no matter where it is present. The value is different, magnitude wise it is different because of its location, but the nature of the gravitational force, it is always directed towards the center. The expression is different, but it is always directed towards the center. So here we have discussed the gravitational force of Earth acting on objects present at different locations. Okay, 3 cases. Okay, so far away from the Earth, on or near the surface of the Earth, or below the surface of the Earth. Okay, so this is the thing.